Hello and welcome to material science. So this subject is all about comparing materials to one another, which one applies best to a particular use. Because in engineering, it's all about like comparing what material suits your needs best, and this is what we do so that we can save money, we can make the best choice, and what can suit our application best. So this subject is just like majority of it is understanding these materials so that you can make a better informed decision. Yeah. Um, okay, so there's like a bunch of like properties on materials that we can compare for particular applications. We can pick like different properties like strength, even though that's a pretty vague term. We can pick stuff like hardness, which sounds hardness, which sounds a lot like strength, but they're actually quite different. You can talk about properties like cost. You know, you can talk properties like weight, uh, or how heavy it is. So let's weight, but like not just weight, maybe something like density, because a kilogram of foam is kind of different to a kilogram of steel. You know, so there's a whole lot of properties that we can, yeah. So you have dot dot dot. There's a whole lot properties. Yeah, there's a whole lot of properties that we can pick between different materials. Yeah. So the idea of the subject of material subjects, just in university, is to learn how to decipher these and figure out what is best for your application, or at least understanding these, maybe on a scientific level. All right. So starting off, let's start off with a concept: strength. So if you go up to a material scientist and you ask them what is to them the strongest material, more often than not they'll reply to you with another question. What kind of strength are we talking about? What kind of strength? And you just be like, duh, it's like the strongest material. But then, if you actually think about it a little bit further, there's different materials that are stronger in different applications. Um, Say if I just had like some generalized material, just like a block, just a rectangular block of something, yeah, I can apply forces in a variety of different ways, and different materials will be stronger in different ways. Say if I pull the materials, so just pulling the material just applies a force across this way, right? There's the other way that I can apply force, which is just the opposite direction, just pushing everything together. Yeah. Another way that we can apply forces is twisting them. Some materials might be just stronger this way. Um, and other materials might be just stronger if you kept one side fixed and then you slid them parallel, maybe like sliding over one another. You know? Each of these types of forces or loads that we can apply on materials have different names. See this red force where you're pulling things apart? This is what we call tension, which is literally just pulling things apart. Um, this yellow one where you're pushing things together is called compression. Just the jargon in material science, compression. Don't mind the R over there. The blue over here is what you call a shear force or a shear load, just shearing, yeah, sliding over. And that green rotation, that's what we call torsion or torsional forces. So you can think like certain materials would be stronger in tension than compression. Say like a rope. Yeah, a rope is greater tension because you can pull it pretty hard and it's not going to break. But if you just press a rope together, then it'll kind of like just slack and like it doesn't actually hold up any loads. Whereas if you compare that to say if you take like a piece of concrete, yeah, um, yeah, if you take like a piece of concrete, you can push it together and it'll take on like a pretty big load. You know, you can stand on it; it will work fine. But if you pull it hard enough, it's much easier to break it by pulling rather than pushing it together. If you take shear forces, certain materials are like pretty weak at shear forces. Yes, say like graphite in a pencil. The way that pencils write is because you apply shear forces on it, and that's how you see the lead on the paper. And you see like torsion. Some materials are stronger and some materials are weak. If you take like a bar of metal, you can twist it and it does pretty fine. But if you take, say, like a bunch of skewers, like wooden skewers, and you twist it, you can, like, sooner or later you can hear and see it snap. Anyway, enough of this ramble above about forces and stuff. Let's get into some more of the jargon and not jargon. Let's go into like concrete thing that we deal with materials. Let's take, for example, consider two metal bars. Yeah, I have like this little skinny cross-sectional area. So imagine like a really thin, skinny, tall-ish bar, and imagine another bar with almost the same dimensions, but it's a bit wider. So it has a bigger cross-sectional area. Yeah. And imagine if I applied like the same force. Yeah, same force, but say imagine we're honing in on tension, but almost the same principle applies for almost all of them. Apply the same force. You would notice that the one with the smaller cross-sectional area would tend to break first. Imagine like imagine this is like a needle, for example, and this is like a big block of steel. Yeah, it might be the same material, but you'd notice that the needle will break first compared to the big block of steel, even if you apply the same force. Yeah. So you notice that like if you want to see like how strong something is or how much load you want to apply to it, rather than like talking about the force itself, you might want to rather than talking about the force, you might want to see how the force compares to the area. So maybe like in a sense like a pressure of sorts. In our case, we don't call it pressure in materials. What we do is we call it stress. Stress. And it's not exactly the same thing that we deal with in uni. It has a different meaning here. So the way that we define stress is literally the force applied on the object. Force. Okay, wait, let's redo this. No, force divided by the cross-sectional area. Yeah. Written in symbols, stress is given by a symbol sigma, and it's just given by force on area. It's as simple as that. So if you applied 1,000 newtons over a square meter, then it has 1,000 pascals. So the units for this, I'll give this a different color. Let's get blue. So this guy is given in pascals. Generally, because materials are pretty strong, you generally have mega or gigapascals. The force is generally given in newtons, and the area, generally you want to go with meters squared, but often we deal in millimeters, so you just convert into meters squared, or you'll have different tricks that we deal with later on. With that, I'll finish up.